Good morning, everyone, and welcome to day 2 of the conference. Welcome to Hall 6. I'm going to be your host for today on Hall 6. I'm Chris Holt. And our first talk straight out of the gate is from Shai Almog. He is the founder of Codename One. He's ex kind of Oracle and Sun with 30 years of professional development experience. Given he's come from the place that talks about debugging or invented a lot of debugging techniques, he's definitely the kind of person that you want debugging your stuff. He's told me that during the pandemic, he picked up some Mysore-style Ashtanga yoga. So maybe if we've got a bit of time at the end, he can give us a bit of tips about working our core. So without further ado, let me hand over to Shai, and he can tell you about practical debugging at scale.
Well, hello everyone. Thank you for that great intro. I'm Shai Almog, as we said. Today we'll talk about some of the cool tools we can use in production and development that aren't a debugger or a typical observability tool. But first, let me say a couple of things about me. I wrote a few books, including one about debugging, which covers all of the topics we'll discuss here. I've worked in this industry for decades in many companies, and as a consultant, I also worked, as we said, at Sun and later on Oracle, etc. You can contact me over my socials, which you can see listed here, and follow me on LinkedIn, Twitter, etc. Also, check out my YouTube channel and blog for videos and posts in this style. This is my April book titled Practical Debugging at Scale. Everything in today's talk is in there and a lot more. I have another book about Java coming out in a couple of months. It will cover Java 8 to 21. So let's jump to the talk. Tools like curl or JQ are remarkably useful. You can and should use them while debugging, but you probably use them while building and testing the features. So you would already be familiar with them and should have some sense of what they do. This talk focuses on tools that you would mostly reach for when debugging. Back in 2004, I first heard about dtrace while working at Sun Microsystems. It became all the rage and always as it was an innovation that Sun was promoting. Dtrace was later ported into macOS 10. It originated on Solaris. Today, there are ports on Windows and Linux as well. Dtrace is a powerful, low-level dynamic tracing framework, but that's just another superlative. And if you never use such a tool and don't have a background in systems programming, you might be feeling a bit confused. What the hell does it do? Well, everything. Do you want to know which files a process opened? Do you want to know who invokes a kernel API and get a stack trace to the caller? Do you want to know why a process died? Do you want to know how much CPU time is spent on an operation? Dtrace can answer all of these and so much more. You might think that Dtrace is one of those tools that will destroy your CPU completely, but here's the killer feature. It's fast enough to run in production with minimal to no performance impact. It was revolutionary when it was launched almost 2 decades ago, and it's still the case to this day. Dtrace needs deep kernel support to work. This is possible on Linux, but requires a special build, so most Linux distributions don't ship with Dtrace. This is mostly a licensing issue. However, Dtrace is available in macOS and Windows. I use the Mac version here. On Linux, strace is more common. We will discuss it soon. It is a very, very different tool, though. On a Mac, dtrace conflicts with system integrity protection, which is a security feature that blocks some interactions between processes, among other things. Under normal circumstances, this would be great, but if you want to run dtrace, this would be a problem. Save your data. This tool can easily crash your machine, and enabling it requires disabling important security facilities on macOS. So if you decide to enable dtrace, make sure you have a recent backup and know what you're doing. To disable the system integrity protection, we can boot to recovery mode. You can do this on Intel Macs by holding the Command R keys on boot. On ARM Macs, we just long press the power button. Then in a recovery mode terminal, we issue the command csrutil disable. Upon reboot, dtrace should work as expected. Note, you can optionally use csrutil enable -- without dtrace. However, this might not work reliably for commands that rely on dtrace. If you wish to re-enable integrity protection, follow the same instructions, but instead of csrutil disable, use csrutil enable. As mentioned before, dtrace is a very powerful tool. There are whole books written about it. It has its own programming language based on C syntax that you can use to build elaborate logic. This is an example of what you can do with raw dtrace and its underlying language. Let's go over the command since it's pretty sophisticated. First, we have sudo. If you don't come from a Unix or Linux background, this essentially means the following will run as a root or as superuser. Dtrace needs system-level access to perform its magic. A dtrace script binds to a probe. Our kernel is instrumented with hooks that match various callbacks. Dtrace connects to these hooks and can perform interesting tasks when these hooks are triggered. They have a naming convention, provider : module : function : name. In this case, the provider is a system call in both cases. No module is given. We grab the write and send to entries. So when someone tries to write to or send to, the following code will trigger. That would be pretty intense and can crash the system, as these things happen a lot, which is why we restrict the process ID to a specific target. This means the code will only trigger for the PID passed to us in the command line. We pass the process ID here. In this case, I passed 9999 for clarity, but we would obviously need the actual process ID. The rest of the code is a standard C-style printf command. If you're familiar with C, this should be instantly familiar. If not, then printf is a command that accepts an arbitrary set of arguments, the first of which is a string representing the output. I can write here hello world and be done with it. But I can also insert variables. In this case, I expect to have 3 arguments. A number, which I will print, surrounded by brackets, followed by 2 strings. This is the number and the 2 strings. The process ID is first. It's a number. It will be printed surrounded by brackets. It's followed by the probe function name and then by the first argument to the probe function name. This is a very powerful tool, but it has a couple of problems. The biggest of which is how complicated this whole thing is. I can read it, but writing these sorts of scripts is hard. As luck would have it, we have a simple solution to the inherent complexity of dtrace. Man pages aren't always helpful, but in this case, they are very useful. We can run man-k dtrace, and it prints out all the commands that are based on dtrace. There are a lot of them. Think of them as ready-made recipes that we can use to implement all sorts of cool capabilities. It's worth your time going over this list to realize what you can do here. The full list is very long, and this tool alone warrants its own book. Let's say you're facing elevated disk write issues that are causing the performance of your app to degrade. But is it your app at fault or some other app? Try read-write by PID. It will print out the reads/writes to the disk. This is a sample output that I cut down for clarity. It can help you see which process is responsible for all the writes or reads. In this case, we can see the security software Sentinel is holding performance down. You can also use bytesize.d to get more specific results on the number of bytes written and their distribution. That's pretty high level though. What if you want specifics? file name, process name, etc. We can use IO snoop to see the IO events as they occur. The IO snoop -a command produces output like this, where we can see every IO operation from every process as they occur and can understand exactly what is going on inside a binary process. This lets us debug the behavior of an app without access to its source code. Imagine what you can do if you know what the app is supposed to do and don't have access to the code. There's so much more we can do with dtrace and the supporting tools. In fact, there's so much I can't possibly cover everything. But searching the web for what you need to find out and dtrace can often point you in the right direction. The strace tool also originated at Sun Microsystems, in this case in the 90s. This isn't surprising though, as the list of technologies originating from Sun Microsystems is absolutely mind-numbing. strace is much simpler than dtrace in both usage and capabilities, for better and for worse. Since dtrace requires deep OS support, it never became an official feature of common Linux distributions, and as a result, on Linux, people use strace instead of dtrace. They aren't interchangeable and are widely different tools despite the name similarity and similar domains. strace is enabled thanks to the kernel feature known as ptrace. Since ptrace is already in Linux, we don't need to add additional kernel code or modules. Typically, dtrace requires deeper kernel support to get around licensing issues on Linux. It's in a separate loadable module, but that still presents some challenges. Working with strace is akin to printing a log entry every time we make a kernel call. This creates very verbose logging for every command you execute. As a result, you can follow what's really going on under the hood of a running process. Nowadays, strace is commonly used in Linux. It's my favorite system diagnostic tool on that platform. It's remarkably convenient to work with since we can run it with no special privileges. Notice that unlike dtrace, you should keep strace away from production environments unless the code is segregated. It carries a significant performance overhead and could bring a production system down. The most basic usage of strace is just passing the command line to it. The output of strace for this is pretty long. Let's go over a few of the lines. This is the strace command. I pass in the actual command as an argument. Notice I don't need sudo or any special tricks. strace just works and doesn't require disabling protections. Every one of the lines below is a Linux system call. We can Google each one of them to get a sense of what's going on. Here's a simple example. Java tries to load the pthread library from the TLS directory using a system call open to load the file. The exit code of the system call is -1, which means that the file isn't there. Under normal circumstances, we should get back a file descriptor value from this API, a positive non-zero integer. Looking in the directory, it seems the TLS directory is missing. I'm guessing that this is because of the missing Java cryptography extensions. This is probably okay, but might have been interesting in some cases. Obviously, the amount of output is overwhelming sometimes. We usually just want to see things like which file was opened and what's going on with our network calls. This will only show the open system calls. That means the app will run faster since it won't log as much, and we can actually read the data since it isn't as an unmanageable amount of output. There are many system calls you can learn and use to track many behaviors such as this: connect, write, etc. This is only the tip of the iceberg of what you can do using strace. As you saw before, strace works great with the JVM. Since strace predates Java and is a very low-level tool, it has no awareness of the JVM. The JVM works like most other platforms and invokes system calls which you can use to debug its behavior. However, because of its unique approach to some problems, some aspects might not be as visible with strace. A good example is allocations. System tools use malloc, which maps to kernel allocation logic. But Java takes a different route. It manages its own memory for efficiency and easier garbage collection logic. As a result, some aspects of memory allocation will be hidden from strace output. This can be a blessing in disguise, as the output can be overwhelming sometimes. At this time, Java threading works well with strace, but this might not be the case moving forward, as Project Bloom is changing the one-to-one mapping between Java threads and system threads. It is landing in Java 21, so this change is imminent. This might make strace output harder to pinpoint in heavily threaded applications. We don't typically think about Git as a debugging tool. Sure, it's a great tool to study the history of a file and narrow down causes, but as a debugging tool, it can be used for one special case of debugging: regression testing, tracing. In this talk, I cover a lot of magical tools, and Git bisect is one of the best examples of such magic. The hardest part in debugging is knowing the general area of a bug. Bisect literally shines a light on the specific commit that caused it, if it's a regression. Before we begin, let's make one thing clear. Bisect is a tool for finding regressions. It does nothing for regular bugs. When we have a regression, we typically know that the issue used to work in a specific release. We would typically have a specific revision where the code worked. We would know that it doesn't work in the current version, but which commit along the way caused the failure. Back in the old days of SVN or CVS, SourceSafe, etc., we used to check out an older version of the repository and test on it. If it failed, we'd go further back, and if it succeeded, we'd go forward to hone in on the specific commit that failed. Those among us who were lucky enough to work with a competent QA department could often pass the task to them. Ultimately, the work was manual. When zeroing in on an issue, we'd follow the sensible search strategy of dividing the number of revisions in half and going to the middle of the set instead of going one step at a time. This significantly shortened the time spent looking for the problematic revision. However, there are still many revisions to search through. At this point, you might wonder why you didn't automate these things. We sometimes did, but since no versioning system was as dominant as Git, these automations didn't last, and I'm not aware of such an automation that made it into any version control system. But Git bisect made it in, and is the automation of this heuristic. Git bisect does exactly that. The simplest use of Git bisect starts with the command git bisect start. This switches us into bisect mode. We can now define the good version where things used to work properly. For instance, in the codename1 repository, I can use the revision that you see here as the good revision. We can mark this revision as good using this command. By saying the revision is good, we say that the bug isn't reproducible in this revision. Once we do, we can activate bisect reversal by marking the bad revision. For most cases, this means the current head revision, which is the default, but we can also specify a revision as an argument to this command, just like we did in the good command. Normally, we don't need to specify revision in the bad command, and I didn't in this case. Once this is done, we can move between revisions by redefining the good or bad revision. I ran these commands on codename1 repo and got the output at the bottom. Notice the value here at the bottom. This is the current revision we jumped to. We can now mark this revision as good or bad based on our manual testing. I marked it as bad. I could have marked it as good, and that would have worked fine. This moves bisect to the next revision we need to test. Every time we move, this number is cut roughly by half. So initially we have 8 revisions. The dumb way to test would be to step over the 8 revisions until we find the bad one. The smart process jumps to the middle. This can eliminate half the revisions with each cycle. That's why bisect says roughly 3 steps remain to finding the problematic revision. This is very cool. We used to do this manually and it was a very confusing process, but this still isn't ideal. I might incorrectly mark a good revision as bad or vice versa. Also, just checking the revisions manually every time seems tedious. Can't we automate this thing? Before we proceed, you can stop the bisect process by invoking git bisect reset to exit the bisect mode. Now that we got that out of the way, going through every revision manually is a major pain. It's better than randomly looking through revision logs and jumping through revisions while keeping our place in our head, but just barely better. Luckily, there's a better way: run. Bisect can run an arbitrary command for us on every revision it encounters. If the command returns 0 as a process exit code, the revision is good. If it returns something else, it's bad. This way, the broken revision will be identified automatically for us with no human interaction. To do this, I first need a test case, a simple shell script that will fail if the test class doesn't pass. I want this to be relatively fast though, so I don't run all the other tests. I can save this shell script and pass it to Git. I can now run this shell script on revisions between the good and the bad revision. This will follow the standard bisect process, so it won't execute on every revision. It will go back and forth until it finds the commit where the test broke. Notice that if compilation will fail because of dependencies within the test case, you might end up with the wrong revision, so keep the tests simple. Java 9 was all about modules. It was the big change and also the most problematic change. It sucked the air out of every other feature that shipped as part of that release. Unfortunately, one victim of this vacuum was JHSDB, which is a complex tool to begin with. This left this amazingly powerful tool in relative obscurity. That's a shame. So what is JHSDB? Oracle documentation defines it as a serviceability agent tool. Serviceability agent is a JDK component used to provide snapshot debugging, performance analysis, and to get an in-depth understanding of the hotspot JVM and the Java application executed by the hotspot JVM. This doesn't really say much about what it is and what it can do. Here's my simplified take. It's a tool to debug the JVM itself and understand core dumps. It unifies multiple simpler tools to get deep insight into the native JVM internals. You can debug JVM failures and native library failures with it. To get started, we can run JHSDB help, which produces the following output. The gist of this is that JHSDB is really 6 different tools. Debugd, which acts as a remote debug server we can connect to, JStack, which is a stack and lock information tool, JMap, which is a heap memory information tool, JInfo, which is a basic JVM information tool, JSnap, which helps with performance information, a command line debugger, which I won't discuss since I prefer the GUI. I will discuss the GUI debugging tool though. The debugd command isn't as useful for most cases, as you probably don't want to run debugd in production. However, if you're debugging a container locally and need to get information from within the container, it might make sense to use debugd. Unfortunately, because of a bug in the UI, you can't currently connect to a remote server with the GUI debugger. I could only use this with command line tools, such as JStack, which I'll cover soon enough. With this command, I can connect to a process ID and expose it externally. You can get the PID of JVMs using the JPS command. I can then use this command to connect to the server with the JStack operation. Notice that the connect argument applies globally and should work for all commands. Some developers experienced issues with the debugd command. I couldn't reproduce the issues when pointing at the right PID. Notice you don't need to use sudo for this command. I also suggest verifying the JHSDB and the JVM are in the same version. Normally, we would run the command directly with the process ID instead of going through a server connection. The JStack command produces a thread dump that you might find very familiar and yet helpful. If you're looking at a process that is stuck on a user machine or production environment, this is an invaluable tool in those situations. With this command, I can connect to a process ID and expose it externally. Some Mac developers experience an operation not permitted error when running these commands. Make sure the terminal application you use has full disk access. Also, try following my previous instructions to disable integrity protection with csrutil disable. Here are a few lines of the output, not everything obviously. Notice a few things of interest. We get information about the running JVM. It detects deadlocks automatically for us. All threads are printed with full stack and compilation status. This snapshot can help us infer many details about how the application acts in production. Is our code compiled? Is it waiting on a monitor? What other threads are running and what are they doing? If you want to understand what's happening under the hood in RAM, then jmap is the command you need to use. It prints everything you need to know about the heap, memory, etc. The command starts with this output. It goes a lot further, but again, I snip this for readability. When you tune GC flags to get better performance and reduce GC thrashing, especially when collecting very large heaps, the values you see here can give you the right hints on whether something is used. The true benefit is the ability to do this on a real process without running in a debug environment. This way you can tune your GC in production based on real environment conditions. If you could reproduce a memory leak but you don't have a debugger attached, you can use the histo flag. This prints a histogram of the RAM, again, snipped below for clarity. You can find the object that might be the trigger of this leak. There are a few other capabilities in the jmap command, but they aren't as useful as those two for day-to-day work. jinfo prints the system properties and the JVM flags. This isn't as useful as the other commands since we probably know those already. However, if you're debugging on a machine that isn't yours, this can be a helpful starting point. It just accepts a PID. JSnap prints a lot of internal metrics and statistics, including the number of threads started since JVM launch, peak number of threads, etc. These are very useful if you want to tune elements such as thread pool sizes, etc. This is the snip version of the output for that command. It's very useful to get a sense of the overhead used in production. I'll skip the CLI debugger. You can launch the GUI debugger with no argument and use the file menu to connect to a core file, server or process ID. Or you can use the standard command line that works for every other command. The amount of capabilities and information exposed in this tool is absolutely fantastic. A lot of it might be too low level if we're debugging from the Java side, but if you're working with JNI native code, you can see the address matching the JVM thread or method in the stack. This can put in context some native code debugging where the symbols might not be exposed coherently. Application performance monitors, also known as APMs, are absolutely great, but they also have some serious limitations. One big limitation is that they are very coarse-grained. Tracing does provide some relief in that sense, but it has its own limitations. Both of them aren't a profiler. Unfortunately, we can't run a profiler in production. When we run it, we get results that make sense for our test data, but not for real-world situations. This line should be one long line without spaces except before the minus jar. I broke it down to fit on a slide. This launches the Java Flight Recorder, JFR. It monitors the application we pass in the last argument and will save the information as we exit. Let's go over the arguments to this command. This parameter represents the delay between the Java application launch time and the start of the recording. We use the S to specify the time is in seconds. I could have used M for minutes, H for hours, or D for days. If I would have written 5M, it would have started recording after 5 minutes. By default, there is no delay. A delay is good because there is often initialization code that would add unnecessary noise to our profiling data. By default, JFR writes the profiling data to disk. We can disable that to further improve performance. When the JVM exits, the recording will be written to disk. The default for this is false. Notice we specified the file name for the recording below. This is optional. Without it, the name of the recording will be constructed from the time and the process ID. Finally, duration limits the time of the recording, in this case to 60 seconds, with similar time settings as we had on the delay parameter. The default is 0, which means there is no duration limit. Limiting the time JFR runs can be useful if we want to grab a few metrics and stop. The impact of JFR is very low. It can be as low as 1%, which is fantastic. With these options, we can ensure it will be even lower. JFR is really a low-level observability platform. It monitors over 170 different events in the JDK, and we can use that for performance or troubleshooting. But we can also activate it dynamically as needed and start pulling telemetry data without the typical overhead we get when working with an APM. We can also create our own application-specific events and provide low-level information about our application to improve both performance and reliability. Java Mission Control, JMC, used to be a part of the JDK, but is now a standalone project and distribution. You can check out links in the GitHub repo for the various JMC implementations. Here we see the Azul version of JMC showing us the results of a specific run. The level of detail that we can dig into with JFR are fantastic. We can tune many settings related to JFR and the events it tracks, but this is a subject for an entire talk in its own right. Wireshark is a free open source packet sniffer and network protocol analyzer originally developed by Eric Rescorla and Gerald Combs. It supports capturing packets on practically any network interface or protocol you can imagine and is an invaluable tool for in our debugging arsenal. Wireshark displays packets in a tree structure called a proto view. This allows easy identification of protocols and ports used in the current session. It is very similar in basic functionality to TCP dump, but the graphical front-end makes it much easier to work with. Capturing raw network traffic from interfaces requires elevated privileges on some operating systems. This caused security issues in the past and could be a serious risk. A more secure approach is using a tool like TCP dump to capture packets into a file. We can then open the file with Wireshark in user space with no special permissions. Both tools are highly synergetic and useful together. Many users of this tool do very low-level networking work, security, browser development, etc. As a result, most of the tutorials and documentation is geared towards developers doing system-level development. This is a shame, since this tool is remarkably helpful even to a high-level application developer tracking web requests and web service dependencies. To be fair, the network monitoring tool built into browsers would probably satisfy most application developers. Both Chrome and Firefox have amazing tools that show the flow of a network request. These should be your first recourse when possible. Wireshark makes more sense when you can't resolve issues with the existing tools or are building an application that isn't a standard web interface, for instance, a native mobile app. In the past, I used it to discover a case where a native application was failing when the server returned chunked HTTP responses. This requires inspecting successful and failed requests to understand the differences. You can download and install Wireshark from their website. It's open source and free for use. Notice that there are separate steps to install command line tools, etc. So I suggest reviewing the instructions. Once you install and launch the application, you would face this UI. Here we need to decide which network interface we wish to capture. This can be confusing if you don't come from a networking background. You might debug a local server and assume that you need to debug the EN0 interface. This isn't the case. If the server is running locally, you should debug the loopback. Look at the activity graph on the right-hand side. This shows you instantly which interface is active and which one isn't. You probably only care about active network interfaces, so it has to be one of those. But even when we pick the right interface, the challenges are still severe. Wireshark is a packet capture solution. It doesn't distinguish between apps. We get a lot of noise when connecting to an interface. Once we pick the loopback, we can see the full data. As you can see here, it's a constantly updating screen. The volume of TCP traffic is pretty big, and I'm not doing anything yet. All of that is just background noise that's interesting to dive into in our spare time, but probably not what we want to look at when we're trying to narrow down a damn bug. Luckily, we have display filters that let us remove noise by focusing only on the specific port which we're interested in, with the condition tcp.port equals 8080. Notice that my server is running on that port, which makes it pretty easy to filter everything else. This brings down the noise considerably, as you can see here. Still, there's a lot of noise because of the protocol. Notice that Wireshark is smart enough to recognize and even highlight the HTTP request I made to the server. Assuming I don't care about nuances of TCP, I can further reduce the noise by adding an HTTP condition, by adding HTTP to the previous condition. This will limit everything to only HTTP requests and responses. Again, very useful stuff that can have a big impact if you're dealing with many HTTP requests and connections. The display filter syntax is pretty powerful and supported by auto-completion within the filter bar. You can read about it in the user guide. You can filter by IP address, not as useful for loopback, source port, hostname, protocol, content, and so much more. This is just the start though. You will notice the second entry in the response from the HTTP server, and it's marked as JSON. Wireshark detects the response type and displays it conveniently, as you can see here. On the bottom portion of the screen, we can see the raw packet display, which is typical for sniffer tools. In the bottom left corner, you can see the hexadecimal value returned from the server. On the right, you can see the matching ASCII or UTF-8 characters matching the hex. This is readable, but might be a bit unpleasant for developers that aren't accustomed to debugging network traffic. If you look one level up, you will see a tree marked as array. This is the JSON array from the response. To be clear, Wireshark detected the HTTP protocol, then detected that the response type was JSON. It then parses the JSON and displays it as a tree for you to read conveniently, even if the packet is minimized and obtuse. When I make a selection within the tree, it highlights the place in the packet so we can inspect the surroundings and see that everything is in order. This lets us instantly see what went on when connecting to a server or client and act accordingly. I'd love to go into more details about Ethernet networks, decrypting HTTPS, debugging devices, and other complexities, but this is mostly the pain of configuring OS-specific settings, browsers, and the whole mess of things to look into the SSL traffic. Personally, I try to disable security for debugging. It makes this much simpler, but sometimes there's just no choice. Thanks for bearing with me. I hope you enjoyed the presentation. Feel free to ask any questions, and also feel free to write to me. Also, check out debugagent.com, my book, and my YouTube channel, where I have many tutorials on these sorts of subjects. Thank you all.
Thank you very much, Shai. Apologies to those who are seeing a stuttering Shai as on his webcam, but hopefully the actual presentation was as smooth as it looked for me. We've got a good question from Morgan here, which is, do you have any recommendations for other tools if you're working in a non-Java world? I know you covered dtrace and strace.
Most of these tools are applicable to non-Java world and have the last one I discussed, Wireshark and TCP dump, are indeed global. Dtrace, strace are all applicable to everything. Most of these tools have some equivalents in other platforms, so not as robust. Java is kind of, in terms of observability and production management, it's kind of in a league of its own. But a lot of environments are copying some of the concepts, and specifically around management tools. So, for instance, one of the things I didn't have time to get into is management tools like JMX and things like that, which exist universally. Just in Java, they're more accessible and more commonplace. So if you're using a management server, which is a pretty standard backend solution, you can also use it for debugging and inspecting runtime components and things like that in production. And there are many off-the-shelf tools there from big vendors. Most of the tools that I mentioned, though, either have equivalent in other worlds that aren't JVM world. By the way, they're applicable to all JVM languages as well, but have equivalents in .NET and Node, etc., although not as mature.
I've got to say that this is an incredibly timely talk for me, because yesterday we were faced with an application that was written in Java by other people, out of memory all the time, and falling over in ways that we just didn't understand. We are running it in OpenJDK, and I just wondered, given that you mentioned that JHSDB was for Hotspot, is that also applicable to OpenJDK and other JDKs?
Hotspot is part of OpenJDK, so
right,
works there great. It's everything I showed there was mostly running on Azure, which is an OpenJDK distribution. So it works on OpenJDK. It's all open source. It's all free. Every single tool that I listed there. So
excellent.
You can use them all in production. No licensing to Oracle. JFR in the past used to be a commercial tool, and so was JMC. And there's lots of, if you Google it, that you'll see some things, even stuff that I wrote about the commercial pitfalls of this. But that has changed since then. And these tools are 100% free, and you can download them from free vendors like Azure and Adoptium, etc.
Wonderful. That'll be great news for my current clients. You showed us at the end there Wireshark. And one thing that I know as a web developer myself is you were showing HTTP traffic, but obviously, you know, with HTTPS, it'll be encrypted over the wire. Is there anything that you can point us to that might help us debug HTTPS or otherwise encrypted traffic?
Yeah, I mentioned that in the talk. I just went a bit fast that I skipped that because it's really hard to do that and explain it. That's why I also recommended to use the browser-based tools if you can. This is sort of the last resort when you can't use the browser-based tools. So for 99% of the work, when I need to do something of that type, I just use the browser, or even use just curl or Postman and stuff like that, and try to reproduce stuff with going out into the actual Wireshark and testing things there. But if you do need that, then you can get the certificate and install it into Wireshark and configure it there. There's sort of a wizard that walks you through that. It's a bit a painful process. So it's not something I recommend for for your day to day. It's the sort of last resort thing. And the reason I didn't integrate it is because it would have taken me, I think, 10 minutes just to go over the process and get it, just explaining it and all of the nuances that might apply.
Well, fantastic. We have run out of time. I'd just like to say at the end that I did spot your South Park Easter egg in there, in the Wireshark output. So thank you very much, Shai, and come back in a few minutes for our next Hall 6 talk. Thank you very much.
Thank you all.
This is all we got. Remember the revolution in our minds. This is all we got.
Lock me out of this life institution. I am angry and high on illusions. Yes, I hate, but it's not a solution. Try my best, buddy, I'm just a human. Oh.